Hi, Lester, Wish Your Engineer. Once upon a time, a long time ago, we used classical mechanics to describe all motion of various objects, from human beings to cars to apples dropping off trees to planetary motion. It's often called Newtonian mechanics because the earliest development of classical mechanics were based on physical concepts and mathematical methods developed by Sir Isaac Newton in the 17th century. Classical mechanics works just fine at describing objects in motion under most conditions. However, when certain conditions are met, such as observing the motion of very tiny objects like atoms or subatomic particles, dealing with motion close to the speed of light, or dealing with objects at certain extremely low temperatures, classical mechanics becomes inaccurate. Strange phenomena start occurring under these conditions that can no longer be described by classical mechanics and that do not make much intuitive logical sense. Phenomena such as wave-particle duality and quantum entanglement. So another theory was developed to explain the discrepancies between observed phenomena and classical mechanical predictions, quantum mechanics. As it turns out, most of classical mechanics can actually be derived from the basic ideas and principles of quantum mechanics. In actuality, classical mechanics, what we are used to observing on a daily basis, is actually nothing more than a special case approximation of quantum mechanics that is only really valid under special conditions and at macroscopic scales. I will not get into the details of both classical and quantum mechanics in this video, since it's not really relevant. Classical mechanics is a bit like an oversimplification of quantum mechanics. What I wanted to do with this is to illustrate an oversimplification that appears to be universally valid until it is observed in more detail under specific conditions. As an aside, when I was studying second year physics at university, we studied both Newtonian mechanics and quantum mechanics in tandem as part of our course. It was an eye-opening comparative study. Both approaches can become quite complex mathematically. And when I walked into the final quantum mechanics exam, I had a mental blank on all of the basic formulae and theorems. But I fortunately managed to keep my cool and made a couple of basic assumptions in the beginning of the paper, and from those assumptions I managed to derive all of the major theorems from first principles, and ultimately I achieved a passing grade on the paper, which I consider to be a great personal triumph of mine because mathematics has never been one of my strongest suites. So what if I told you that everything you currently believe about human movement may be fundamentally flawed? That a little bit like the story of classical mechanics, we are most often depending on a gross oversimplification of human movement that breaks down under certain conditions. Most people, even some professionals in the field of physiology and the study of human movement, oversimplify the human body into a system of rigid levers operated by the ratchet and pulley system of the muscles and tendons. Now, this is a useful approximation which works relatively well under most circumstances, a bit like classical mechanics, but breaks down under certain conditions. Here, let me show you something that some of you may have seen before but never applied to human movement. So this is a raw egg. This is a little experiment that's sometimes done with children, just to show them how you would be able to tell the difference between a raw egg and a hard-boiled egg. So this is a raw egg. I'm going to spin it, and then I'm going to stop it, and we'll see what happens to it. Would you look at that? It continues moving. And of course, it continues moving because it's raw, and the fluid inside, once the fluid starts moving, even though I might stop the external shell, the fluid is still moving. And when I stop it and then take my finger off the egg again, friction between the internal surfaces of the egg and the fluid in motion then starts dragging the shell along with the movement as well, so that the egg continues to move. And our bodies are a little bit like this egg because they contain so much fluid. Eggs are composed of approximately 76% water. An adult human being is composed of approximately 65% water. I've used the Wikipedia article on body water as a reference here. The article indicates that most of animal body water is contained in various body fluids, which include intracellular fluid, extracellular fluid, plasma, interstitial fluid, and transcellular fluid. It goes on to quote from Netter's Atlas of Human Physiology, stating that the body water is broken down into the following compartments. Intracellular fluid, which is 2/3 of body water, is fluid contained within cells. Extracellular fluid, which is 1/3 of body water, is fluid contained in areas outside of the cells. And that includes fluids such as plasma, interstitial fluid, which is actually 4/5 of extracellular fluid, so the great majority of extracellular fluid is an interstitial fluid, and transcellular fluid, which is fluid contained inside organs. If so much of the human body is made up of water, could it be that the approximation of a rigid frame that is so often used to describe human movement can be inaccurate under certain conditions? Let me show you an example of something that would be very difficult to do if my body obeyed the rigid frame approximation.
What I want you guys to do is I want you to just, I'm going to hold my arms out like this. I want you to just come up underneath my arms and just lift me. Okay. Lift me off the ground. So you come up underneath and just lift me up. All right, good. There we go. All right, and you can put me down now. Not so. I'm not so heavy. All right. Okay. Now I'm going to do it again. This time I'm going to try and do something a little bit different. Okay, so I'm going to ask you guys to lift me again. Okay, so what was I doing there?
Shifting away.
How?
Because you see.
Now, there are a lot of things that I'm doing in this demonstration to make myself appear heavier to my students. Things like reacting to my students' incoming forces by adjusting my structure dynamically to bridge force down to my center of gravity. However, one of the things that I am doing here is lowering my center of gravity internally. How do I do that? Well, I do that by consciously controlling and adjusting my internal fluid volume, flow, and pressure. If I were a rigid system of levers, I would not be able to do this. We are not just a rigid frame. We are a complex system composed of a relatively rigid endoskeleton in combination with a substantially flexible fluid-filled hydraulic exoskeleton. Most of you will have seen slow motion footage of human collisions in which the body behaves a bit like a jelly or a fluid-filled sack. Take a look at some slow motion footage of me punching a bag, and you'll see this kind of hydraulic interaction along my arm, which is exposed in the footage. Because of the inherent complexity of a relatively rigid endoskeleton combined with a flexible hydraulic exoskeleton, there are a lot of interesting interactions between these two systems that leads to types of motion that could not be predicted by the oversimplified rigid framework model of human movement. In fact, we believe that the traditional concept of chi is heavily related to developing a conscious control of the hydraulic exoskeleton of the human body. By controlling how the fluid moves in the human body, all kinds of phenomena related to fluid mechanics become possible. And these phenomena may include things such as lowering the center of gravity by redistributing fluid, absorbing incoming energy and force by controlling fluid pressure levels, amplifying sustained forces through increasing or decreasing fluid volume and pressure, and creating pulses or waves in the internal fluid that can be harnessed to amplify impact. Well, I hope you enjoyed this shorter video, and I'll see you next time. Cheers.